we're going to start doing electron configurations. So electron configurations just show us how the electrons are distributed in the orbitals. It gives us an idea of where the electrons are, because remember, it's all about the probability of finding an electron. So we know, we have an idea of what orbital they're in, where they're located, just not the exact location. So the electron configuration, we're going to be using N. So N is the shell, the energy level. So that's the 4 there. And then P is going to represent, or the letter will represent our subshell, the type of orbital. And then the superscript tells us how many electrons are in that subshell. Okay, so I'm going to start with some examples here. Okay, so first we have helium. Helium has 2 electrons. So remember, we start at the lowest energy state possible, which is the 1s. So we're going to write 1, that's our shell, s is our subshell, and we have 2 electrons, and we're going to put those, for goodness sake, those 2 into the s subshell. So that is the electron configuration for helium. That's it. Then we have oxygen. Oxygen has 8 electrons, and I'm just getting these numbers based on their atomic number off the periodic table. Okay, so we're going to start at the lowest shell again, 1s. S can hold up to 2 electrons, so I'm going to put just 2 in there. And then we move on to the next energy level in subshell, which is 2s. And again, S can hold up to 2 electrons. And I've used 4 electrons so far, and I have 4 more to go. So then we go from 2s to 2p, and I put the rest of the electrons in 2p. So remember, p can hold up to 6 electrons, but since I only had 4, that's all I'm going to put into the p subshell. Okay, let's do sodium. Sodium has 11 electrons. So again, we start at 1s. We're going to put 2, 2s, put 2, 2p. So in 2p, we're going to fill it up. We're going to put 6 electrons. So far, we've used 10 electrons. So 2 in the 1s, 2 in the 2s, and then 6 in the 2p. That equals 10 electrons total. I just have 1 more, and we're going to put that one in the next energy level, which is 3s. We just have 1 left. Okay, one more example here. Iron, and iron has 26 electrons. So we'll start at 1s, put 2 electrons, go to 2s, 2 electrons, 2p, 6 electrons. Okay, so again, I've used 10 electrons so far. I've got 16 to go. So then we can go to 3s, put 2 electrons, and then 3p is next. And I can put 6 in 3p. And then we go to 4s, and I can put 2. And then 3d is the next one. So remember, D subshell can hold up to 10 electrons, but I only have 6 left. I've used 20 so far. I only have 6, so I'm going to put 6 into 3d. Okay, so we were looking at our last quantum number at the beginning of this and said that electrons have opposite spin. That's pretty much what the Pauli exclusion principle tells us. It says that no 2 electrons in the same atom can have exactly the same energy. So because these electrons have opposite spin, they don't have the same energy. So that's what Pauli exclusion principle is telling us. So there won't be an electron with the exact same quantum numbers. So we're gonna add all these together and look at N again, which is the shell, L the subshell, ML is the orientation, and then MS is the spin. So just to give an example, so with beryllium has 4 electrons. So we'd put 2 in the 1s, 2 in the 2s. So that would be the electron configuration. So we're going to do the quantum numbers for 2s too. So first of all, the N is going to be our shell, which is 2. The L value is going to be our S, and we know that 0 signifies S. And then the ML value, we know that ML is from a negative L to a positive L. Since we just have a 0 for L, it's just going to be 0. And then our MS value, so we're going to rewrite this as a line to show the orbital. 1 electron going up, 1 going down. So one of our electrons is going to have a positive half. So the other electron is actually going to have the exact same quantum numbers, except for the MS value is going to be a negative half.